So next speaker is Sreejith Jaya, and he is going to talk about group equivalence CNN on the quantum diamond model.
Okay.
What do you say?
Okay. I'll talk about the some group symmetric neural networks on which can be applied to find the ground state of the quantum diamond model. We'll present some results. The work is almost complete. We are in the process of writing up. This work was in with PhD students and an undergraduate student at IISc Pune. Yeah. So very quick introduction to quantum diamond model. The quantum diamond model is a quantum model of a system where the basis states are given by classical dimer configurations, fully packed classical dimer configurations. And here I'm looking at two-dimensional quantum diamond model. And the Hamiltonian for the system is given by this, where there is a kinetic energy term that corresponds to a ring exchange of the dimers on a plaquette, and the potential energy corresponds to an energy cost or gain associated with parallel dimers on a plaquette. This has been used extensively to sort of model resonating valence bond physics. It is one of the simplest models of kinetically locally constrained Hilbert space. And the best way to study the physics of the system so far has been quantum Monte Carlo. And the quantum Monte Carlo itself is a little hard because the local the Hilbert space is locally constrained. Standard quantum Monte Carlo moves do not work in this case. Although in the case of finite temperature, we've been able to use stochastic series expansion to map out the phase diagram of the system. The phase diagram consists of a columnar ordered phase at small values, small negative values of V. There's a staggered phase at large positive values of V with a Roxer-Wilson point at V equal to 1. And at high temperature, there is a Coulomb gas phase. Essentially, getting any answers at t equal to 0 is hard because the quantum Monte Carlo just ceases to work at t equal to 0. The question that I'm asking is quite simple. Can I write down the ground state of the quantum diamond model as a neural network? And it seems somewhat natural to think about this because neural networks are good at doing image classification and functions of images. And like if I treat the diamond model as an image, can I get the ground state wave function, which is essentially a function from the diamond model image to a complex number? The question is, can I optimize a neural network that can accomplish this task? The strategy is quite straightforward. Conceptually, it's not very difficult. I treat the neural network as a variational state with the variational parameters being the weights and biases. This is a little challenging, but it's a numerical task, which is to construct a function that can estimate the energy expectation value of a given variational state. For this, we use Monte Carlo, and assisted by some of the algorithms that are efficient on the diamond model. Then we use gradient descent on the energy function to get the ground state. In principle, this is straightforward, but the question is, can this be actually used? And that's what I'll try to discuss here. If we naively use a neural network, it doesn't take advantage of the fact that the system has a lot of symmetries. In particular, I'm going to use the square lattice diamond model. The square lattice diamond model has many symmetries. It has a dihedral group symmetry, mirror symmetry, fourfold rotation, etc. In addition to translation symmetry, can I use those symmetries in the neural network itself? That brings us to the idea of group equivariant convolutional neural network. Roughly, the idea is this: if I think of a convolutional neural network, which essentially is like block decimation that we learn, almost like block decimation that we learn in basic renormalization group discussion. We think about a convolution of using a small kernel of the actual degrees of freedom. And you can, if you repeatedly do a convolution, you can get more and more coarse-grained description of the image. And if I take the sum of all the pixels at the last image, then I get a number. And this function that takes the initial image to a number, you can show is translation invariant. If you translate the image, the final number turns out to be the same. So the standard convolutional neural network, which essentially is doing this, is a translation invariant operation. F of translated image is the same as F of the original image. Such a CNN produces a k equal to 0 translation invariant wave function. It can be then used to represent the ground state of translation invariant lattice systems. The square lattice has more symmetries, the mirror reflection, fourfold rotation, etc. The P4M symmetry. The question is, can I generalize the notion of CNN to a bigger group? And the idea, there were two images here, but only one of them is working, sorry. So this is the standard way to think about convolutional neural net convolution. Basically, I have a convolution kernel which is used to locally average the value of the degrees of freedom to get the next image. I can think of the same thing in a different way. The kernel is held fixed, and I'm applying a group transformation to the image, and then applying the kernel on that part of the central part of that image. And with that, I can get a new image. Now, this new image is now a function of the group transformation that was applied to the image. And therefore, I have, after convolution, I don't think of it as a new function from the space to degrees of freedom. I think of it as a function from group operations to real numbers or complex numbers or whatever the degrees of freedom is. So that can be mathematically written this way. The precise details are not important. Finally, if I sum over all the group elements, because this is a function of group, if I sum over all the group elements, this quantity can be shown to be in the trivial representation of the group. Here it's a translation group. The generalization to general groups is straightforward. I think of the kernel as held fixed, and I apply all sorts of group transformation, including rotation, mirror reflection, etc., and then get the convolution, and that gives me a function of a general group to degrees of freedom. Oh, now it works. So that was the standard way of thinking about convolution, and this is the alternate way to think about convolution. So basic idea is this. I have a network in the first layer. It takes the image into a function of symmetric group elements. The original image can be thought of as a function from position to various local degrees of freedom. And in the subsequent layers of the neural network, I take functions from group to complex numbers to another function from groups to complex numbers. And finally, in the last layer, I collect all the elements of this network. These are functions from groups to real numbers. I sum over all the group. Instead of summing, if I sum weighted with the characters of the group elements in that particular representation, I get a function. This whole thing looks like a function that transforms under a particular representation rho. We'll be interested in the trivial representation, so the chi, the characters are all one, so it's just sum over g, f of g, that transforms under trivial representation of the group symmetries of the system. Okay, and this is the actual contribution from us. This is the caricature of the actual optimization step. I have a variational wave function. I use, okay. I'll just go to the results. So we can use the directed loop algorithm to optimize to sample the states. And this is an advertisement of the result. This is a comparison with ED for 8x8 system. The diagonal line shows the x equal to y line. The y-axis is log of the coefficient of the ground state using ED, and the x-axis is the log of the coefficient of the ground state obtained by the convolutional neural network. The green, blue, the green, red, and magenta lines show 1-layer, 2-layer, and 3-layer neural network. And as you can see that with 2 layers, you almost get identical x equal to y line. Just to advertise, the dimension of the system is 311 million. So a small neural network with 4,000 parameter is able to capture the 311 million Hilbert space dimensions ground state. Okay, this is so that was the comparison with ED, where 8x8 you could do ED. You can use quantum Monte Carlo to compare with larger systems, and this shows the comparison between quantum Monte Carlo for 32x32 system and the GCN, the group convolutional neural network. The dimension of the system is 10 to the power of 128. This is the comparison of energy expectation value. This is the comparison of some order parameters. This shows the convergence of the ground state energy. The first excited state energy is here. This is the convergence with iterations of the optimization, and it shows that the ground state is reliably obtained. This is 1 minus fidelity shown in log scale. So the fidelity is 10 to the 1 minus 10 to the power minus 3 to a good, so it's a good approximation. We can ask various general questions. The optimization was done with samples taken from the constrained configuration. What does the network say about unconstrained configurations? These have physical meaning. For instance, as the monomer pair correlation can be calculated by looking at configurations that violate dimer constraint. It turns out that the GCNN, even though it was trained with constrained configuration, it can somewhat accurately calculate the monomer-monomer correlation. This calculation is still being done. So this is just a question that will be addressed in our paper, but just advertisement for that. Okay, I'll leave the conclusion slide here. The basic result is that the neural network is able to reliably obtain the ground state somehow, even for systems where the Hilbert space dimension is 10 to the power of 275. And why do these things work? We do not know. There are various conceptual questions you can ask about this, but I'll stop here. Okay, sorry for taking long.
Okay, thank you, sir. Any questions?